All right, section 3 of module 8. So still going through like the theory of process control. We're going to talk about the different types of control modes in section 3. The trade terms, like those trade terms are good to know. If you've never heard of hysteresis, you should know what hysteresis is. I don't have it highlighted, but it's a condition in the system that prevents changes in the input from immediately affecting the output. After delay, the output will begin changing in response to the input. The greater the delay, the greater the hysteresis. So if I had a signal coming from, say, a flow transmitter, like a flow transmitter that's normally 4 to 20 milliamps, right? And say I went from 12 milliamps, which would be about 50%, and it jumped real quick to like 20 milliamps. There's going to be a delay between that signal at the transmitter and then the HMI that the operator is looking at, so that the flow doesn't go from like 50% to 100% immediately. Does that make sense? The reason you don't want that is because if say that was just a little glitch or something happened, like air bubble or something came through there, or got up in the differential pressure sensor, if that saw something that said our flow is 100%, the controller would say, shut that down, right? Shut it down immediately because it's too much flow. Well, the reason they have hysteresis is we're sending that signal back to the controller. Let's make sure that this is an actual reading, give it a couple seconds, and then start making, the controller can say, then start making adjustments if that holds at 100%. Does that make sense? So hysteresis is pretty much a buffer. Whenever you hear the word hysteresis, just think of the word buffer. My first highlight on page 26 is the last sentence of the first paragraph. There are two basic modes of control, or parameters of response, that are applied to control loops. On-off, which is two-position control, and modulating control. So key in on two-position and modulating control. So two-position control would be like, what would be an example of two-position control? Just be like turning a motor on or off, or a pump on or off. That's just whether it's going to run 100% or it's going to run 0%. Right. So if we had like a sump pump somewhere, sump pump usually has a float on it. That float is on-off control, right? That float, as that float comes up, it flips upside down, turns on the pump, and then it goes down, and then flips back over, and it's off. That's on-off control. That makes sense? Modulating control. So if I had a big control valve that can operate between 0 and 100%, that would be modulating control. That's saying like I always say, you got your big tank, you're filling up to 500 gallons of water. You need some water, but not a lot. That control valve can open up to 50% to start giving it some water, and as it gets closer to that 500 gallon set point, that valve will start to taper off like 40%, 30%, 20%. So that whenever it gets close, it slowly gets there, and it's not having to shut off immediately. That makes sense? That's modulating control. So when you think of two-position control, I want you to think of digital. When you think of modulating control, I want you to think of analog. 310, on-off control or two-position control. 310. First paragraph, last sentence is highlighted. The simplest type of controller is a two-position or on-off controller. Technically, what's in the back of your toilet at your house is an on-off controller, right? As the water fills up in the tank, that lifts it up, shuts off that water valve, on-off controller. Neutral zone, page 27. In 311, the neutral zone, coming?
With a chapter 8?
We're going through the rest of chapter 8, yes.
Oh. Okay, then you're recording.
I'm recording, but I will not be here on Thursday. This is the only class you'll have this week.
Oh, okay, because they were showing me a new, okay, let me put everything away and come here.
Okay.
Yeah.
Neutral zone. First paragraph, I've got the second half of that first paragraph in 311 highlighted. So it says neutral zone represents through the end of the paragraph. So neutral zone represents the region of measured variable overlap in which the controller output can either be on or off, depending on the state of the controller output prior to the measured variable entering the neutral zone. When the measured variable is below the neutral zone, the controller output is always on. When the measured variable is above the neutral zone, the controller output is always off. So essentially what that's saying. Your thermostat at your house, starting to get hot, people are starting to turn on the air conditioning and stuff. If we are turning on our air conditioner, right? Say we set our air conditioner to 72, right? 70. Piece of shit. 72 degrees, right? So turn it on. Say it's 75 degrees in the house. Turn your air conditioner on to 72. It's going to turn on your system outside and your blower inside, and your air conditioner is going to turn on, right? Air conditioning gets down to 72. Does it shut off? Not usually. It goes a little bit farther, right? So that's what the neutral zone is. So it's on at 72, but it might get down to 71, and that's where it shuts off, right? It raises back up, and it's like 71. It gets to 72. It doesn't. So this is our set point. I'm going to say this is like 73, and then this is where we're hitting 72. So 72 is our neutral zone. So we get down to 71, it shuts the system off, right? Starts to get hot in the house again, gets up to 72. It does not kick on, gets up to 73, kicks back on, and then lowers the temperature. So the neutral zone is that area in between. Why would you want a neutral zone?
So you don't keep your stuff running consistently.
Not necessarily consistently, but not if I had 72 on and off, like it would cool to 72, it would raise up to 73, turn back on. You would cycle your stuff a lot more. Way more on and off. So the contactors, the capacitors, the motors, like the inrush current of a motor is the highest in the first half a second, right? The more amperage you push through a motor above its full rated load, the weaker that motor gets. So that neutral zone allows you to have less on and off motion. So less you turn it on and off, the longer stuff lasts. Colby, you know how to get into the online book? In the Canvas? So we're doing the second half of chapter 8. The first half is it's in Canvas. We can watch that to catch up on the first half. Go to courses to the left. Modules. Does anyone in here prefer the online book to a print book?
Nope.
I don't understand where they got their, like, they sent y'all, surveys for Follett. They sent them to everybody that's used this stuff, and supposedly 65% of people said they either liked the online book more or didn't care. That is not my experience. Go to that, like, click on that, word, type in 1,000. And now you can go to modulate. So you go, or no, you go.
Is module 110.
Yeah. So we're on page 27, so you're just gonna flip through this 27. Alright. Everybody go to the neutral zone. Makes sense. Flipping over, they're gonna talk about turning stuff on and off. So if, tank level, like this is the actual tank level. And then you can see the water flow being turned on and off. So the tank level's high right here. So my water flow is off. And then you can see my tank level dropping, right? Upper zone. My set point is right here. My lower zone limit, that's what kicks on. So all right here is my neutral zone. Kicks on, stays on all the way till it hits the upper zone, back off, same thing. Same thing as the air conditioning thing that I just said, just a different version of that. They go through like how fast this stuff can happen and stuff like that. I don't find that necessary, like all that's gonna be set up whenever people buy the system. I don't have anything on pages 28 and 29. But going on to page 30. Page 30, the second paragraph on page 30, first sentence is highlighted. One method of reducing the harmful effects of overshoots, undershoots, and system delays is to reduce the width of the neutral zone. If I reduce the width of my neutral zone, what am I also doing? What am I causing for the system? It's gonna turn on and off more. But if you want your stuff to be more like a tighter tolerance and stuff like that, you can reduce the neutral zone and cause that and then cause that. If you're finding stuff, because if you're just opening a valve, open and close, that's not a big deal. If you're turning on a 20 horsepower motor on and off, that's gonna be a problem. Especially if it's like air conditioning stuff, you don't want compressors turning on and off. You either want to run or not run. So that's everything for 310, moving on to 320. Modulating control. What word did I want y'all to think of when you heard modulating? Analog. On off was what? You have analog or
Digital.
digital. Digital's on. Digital is on and off. Binary, zeros and ones, on and off. Analog, 4 to 20, 3 to 15. you have an actual span with modulating control for analog. 320 modulating control, second paragraph, first sentence is highlighted. Modulating controllers contain three basic functioning modes: proportional, integral, and derivative. Okay, for the next several pages, it's going to talk about the different types of control. I'm going to give you my highlights and stuff, and I'm going to talk about it a little bit, but not a lot, because this is stuff like I had to, like in college, I had to go through and do the, like, anybody ever get to where they were doing derivative functions and integral functions in math and stuff? So did you ever use it?
No.
We had to do where we would set up a controller and we would have to figure out the exact right derivative to put in, to get these controllers to work right, or perfectly, because they were teaching us how to engineer stuff. In my experience in the actual plant, not even close to doing that. I never got out of using proportional. So proportional is just my gain. Remember, I talked about like your, you had like your, like this is your set point, and then I talked about how you get to your set point and then it tries to find it. Everybody remember that? So your proportional control is your gain, which I think we talked about this, it's your rise over your run. So the higher your gain, the faster you're gonna get there, but the more overshoot you're gonna have. So the gain is a lot higher, right? That's a horrible picture, but does that make sense? The more proportional you add, the faster it's gonna get to that set point, but if you get there too fast, with modulating control, it'll never be able to find that set point. If you turn your gain up, if you turn your proportional up too much, you'll never find it. It'll just keep slamming the valve all the way open and then all the way closed. So if you ever have an issue, where a system keeps going, like hunting for its set point and can't ever find it, you can go into your controllers and turn the proportional down a little bit and see if that works. Like that's one of the troubleshooting steps for troubleshooting a modulating controller that's having issues finding its set point. But like I said, I'm going to talk about, I'm going to give you my highlights on these and talk about them very little. But if you want to read through these, you can. But in my experience, proportional is the one to mess with. Integral, I never messed with anything that had to have integral control. So proportional, gain or P control, 321. The whole second paragraph is highlighted in 321. Another type of control is available in which the final control element is throttled to various positions that are dependent on the process system conditions. A proportional controller, also known as a gain controller, provides a steepless output that can position a control valve at intermediate positions as well as full open and full shut. This is accomplished by a lower gain with the controller. Bottom left paragraph on page 31, second sentence is highlighted. Another way to describe proportional control is that it gives a linear output to input relationship. Then it's going to go through all the math to find what your gain is. Going into, like, flipping over to page 32 and 33, they can find what your gain is and how fast you're going to get there. So if you look up here, you can see my gain is 0.5. So this, see how long that takes? That takes. So this is your float level, this is your valve position. But it takes longer to get to your 1 inch open if your gain is set to half. If you set your gain to 1, it's gonna get there a little bit quicker. If you set it to 2, it's gonna get there a lot quicker. So that's saying you're going from 4 inches to 0 inches open. The higher the gain, the faster it's gonna get there, but the more chance you have to overshoot your set. Page 34 and 35. So what I'm gonna say about integral. And these are proportional, integral, and derivative. One way I want y'all to think about them, it's more and more, you know how, like a scope of a gun, you have like the coarse adjustment and then the fine adjustment. That's kind of like how this is working, like your coarse adjustment, so your like big time adjustment is your proportional, and then integral is like your fine tuned adjustment, and then derivative would be even more so into that. So the tighter and tighter tolerance of control you want, the more you add. So for integral, like say this again, say that's my set point. Then my process finds that, finds my steady state. And then see, most processes, if you don't add integral, say this is 50 gallons of water. See this right here, that might be like a quarter gallon of water or something like that. It's gonna be off just a little bit, because everything's not calibrated exactly right, or it's not responding exactly correctly. Integral will take care of that. It constantly looks for the difference between the set point and the process value. So whereas I have a 100 gallon tank filled at 50 gallons and it's at 49.75 gallons, I don't care. Like, it doesn't matter that it's at 49.7 gallons. But if I had something with a little tighter tolerance, like a nuclear power plant or something that has to do with cooling, that cooling has to be exactly perfect at a nuclear power plant, and there's gonna have more automation with that. Does that make sense? Those big tanks you see at all the refineries and stuff, they don't give a crap if they're a quarter inch off. I mean, it probably matters. It's probably hundreds of gallons of whatever's in those tanks, but it probably doesn't, in the long run, it doesn't make that big of a difference as far as what they're controlling to. But integral will take care of that offset. My highlight for 322 is the first sentence. Integral control, also known as reset or I, describes a controller in which the output rate of change is dependent on the magnitude of the input. Derivative control, 323, rate or D control. Second paragraph, first sentence is highlighted. The device in the controller that produces a derivative signal is called the differentiator. 323, second paragraph, first sentence. The device in the controller that produces the differential signal is called the differentiator. Page 36. So proportional plus integral, so PI control. So this is just adding a little bit more control. Right hand side of the page 36, second paragraph, first, that all one sentence, first sentence. The combination of the two control modes, the proportional plus the integral control mode, combines the immediate output characteristic of the proportional control with the zero residual offset. I want to key in on that zero residual offset characteristic of the integral mode. So that offset, like I was talking about, that's what it's talking about with the integral mode. The integral is going to take care of that. So the PI is going to get you to the set point quickly, and it's also going to take care of the offset for PI. So you can see if I had proportional only, like both of these are steady state, then this is my new set point. Proportional only will go up, but it's going to have an offset in between the two. But if I have proportional plus integral, it'll get there. That's a pretty steep gain, and then eventually it'll eliminate that offset. I don't have anything on pages 38 and 39. Right. I also don't have anything on pages 40. I don't have anything through the rest of the section. So if you guys want to read through like this, the different types of controls, you can. But like I said, the more you add, that's just like it's going to do proportional plus derivative controllers, proportional plus integral plus derivative controllers. So that PID controller that we have on the flow and level transmitter, that's a PID controller. Like there's actually a lab that I had y'all skip because it takes so long. Like you have to sit there for 10 minutes for each input you put in there and time it and see how fast stuff happens and whatnot. And you actually physically go add those in, but I just didn't find it a benefit. We have extra time next semester and stuff, and that's something you want to do and focus on. I can walk you all through that with extra time, or individually walk you all through that with extra time, but it takes too much time out of our lab. There's more important stuff to go through. But yep, I'm gonna do the same thing I did on what is today? Tuesday. Same thing I did on Thursday. I'm just gonna keep going. So with everybody in here now, there is no class on Thursday. I won't be here. We've got finals week is the week of the 8th. So we've got 4 more classes technically for this. And really I'd like to be done by the 9th. So no class on Thursday. I'm gonna go through the rest of this chapter tonight. And your homework will be to get everything done for the beginning of class next Tuesday. We're gonna go through that, pretty much be ready for the test, take the test on Tuesday, and I'm gonna go through the last chapter of the test. I'm gonna give you that for homework to be done for Thursday. Take the test on Thursday, the rest of Thursday and Tuesday are gonna be labs. Then we're gonna be done for the semester. And like I said, we're not gonna get done with all the labs that we have to do. You're gonna be done with all the labs technically for instrumentation 3, but I have y'all do a little bit more stuff. But that's why, like, if you have not yet, go ahead and sign up for instrumentation 4, and those labs are just gonna carry over. And just like this book has 9 modules, instrumentation 4 has 7 modules. And it's pretty thin book, so we go through those fairly quickly. We're in the lab probably 70 to 75% of instrumentation 4. So we go through the book and stuff fairly quickly, and we're in the lab the rest of the time. So that way, it usually happens where I spill 3 over into 4 and stuff like that. But We're gonna start messing with that. We're also gonna start messing in the methanol plant. Out back, they're finally starting to get that to where that can run. I just had the instrumentation 4 class. Right before this, we went and shot loops. I think we shot 20 loops last class, and only 2 of them are bad, so they're trying to fix that to where we can work out there and do some real live stuff. So that's another thing we're gonna be doing next semester as well. Does that make sense for the rest of the semester?
Yes, sir.
All right, so you don't have to do section 3 yet, but it is gonna be, you have to have all this done for class next Tuesday. I'm giving you a whole class off. You should be more than enough time to get done with everything. So, section 4. Actually, let's see how many of these we can get. I don't know how quick y'all have it. So, responds rapidly to disturbances, has no offset. What type of control is that? What type of control takes care of offset? So you have proportional, integral, and derivative. You can combine them anyway. You can have anything except for integral and derivative together, or integral by itself. So responds rapidly to disturbance, has offset, is gonna be, oh shit, it gives you all. Okay, I did it one by one. So that'd be proportional plus derivative. Integral is what takes care of the offset. So has minimal offset, but it responds slowly. So that means the gain is bad, but it doesn't have an offset. So that's I. Average response to disturbances, but it has an offset, that's just P. So that responds rapidly. The derivative actually helps it respond faster to disturbances. PID responds quickly to disturbances and has minimal offset is PID. Average response to disturbances, minimal offset, PI, can't be used alone, is derivative. Kind of makes sense? Types of control applications. First paragraph, last sentence is highlighted on page 47. High-speed reactions that occur in many modern industries cannot be successfully controlled without rapid responses made possible with automatic control systems. This would be true, like where I come from, in the steel mill. I told you all we made big coils of steel and stuff like that. In the reducing mill, they just ran that big coil of steel back and forth. And each time they ran it, they pinched the rolls a little bit closer together, and that way it flattened out the steel, which made it longer. But they would run at they could run up to like 3,000 feet a minute, which with a big coil of steel is fast. So that thing is moving so fast and has to be so accurate in the exact size opening of the rollers. That couldn't be done without automatic control. Like no human can see that fast to adjust stuff or anything like that. So these types of controls, a lot of the stuff that we're able to do today is I mean, even whenever you look at like the technology they used to go to the moon the first time is, I'm pretty sure like this calculator has more computing power than the first ship that went to the Mars. Like it's crazy what they were able to do. But high speed stuff is what's wanted in a lot of this. Typical temperature control loops, electronic temperature control loops, 412. They talk about electronic temperature control loops. My first highlight is second paragraph, first sentence. A resistance temperature detector, an RTD, senses temperature in the tank. This is your RTD, senses temperature in the tank, resistance temperature detector. Skip a sentence, and then the next 2 sentences are highlighted. The temperature transmitter, or TT, performs the functions of the transducer and the transmitter of the basic control loop. It converts the temperature-dependent resistance value of this sensor into an electrical signal proportional to the measured temperature. So you got your RTD, it goes in your temperature transmitter. So this would change this from a resistance reading to probably like a 4 to 20 milliamp signal, right? So then you have your TI temperature indicator that just shows what the temperature is to the operator, and then you have your controller. So your controller is saying, hey, this is, the temperature needs to be 500 degrees, we're at 400 degrees, so it turns on your triac, which turns on, this is a symbol for a resistor or a heater to heat this, whatever's in here back up. Does that make sense how that loop works? The next paragraph, first sentence is highlighted. The temperature controller compares the actual process temperature to the desired temperature, which is the set point. Four, two, one. Pneumatic pressure control system. I've got the first half of the first paragraph on page 49 highlighted. So the beginning all the way to where you see PC in parentheses. The pneumatic pressure control loop shown in figure 51 is designed to maintain a constant pressure within the closed tank by controlling the nitrogen supply and vent valve. A locally mounted pressure transmitter, or PT, senses pressure. The transmitter sends a signal to the pressure recorder and the pressure controller. So, going through this one, I've got a pressure transmitter, detects the pressure in the tank. So I want to keep this tank at a certain pressure, and I'm adding nitrogen to this tank in order to raise the pressure, or I'm opening this vent, to lower pressure. These are pneumatically operated valves. Remember, 2 slashes is pneumatic. So pressure transmitter senses pressure in the tank. Pressure recorder records the pressure that's in the tank. The controller looks at the pressure in the tank and sees whether if the pressure is low in the tank, which valve is it going to open, A or B? It'll open A, because it'll add nitrogen. If the pressure's high in the tank, it'll vent it out through valve B. That makes sense? So valve A adds nitrogen to the tank, valve B vents nitrogen from the tank. So that's a pneumatic pressure control loop. Last 2 sentences in 421 are highlighted. In this application, both the supply valve and the vent valve typically fail closed. This prevents the system from either overpressurizing or completely depressurizing. I will tell you for this test, these couple of sections are the most missed on the test. So the pneumatic pressure control loop, the way the valves fail is important for this pneumatic control valve, and then the different parts of it are important. So how the valves fail for pneumatic pressure control system, the different part is a highly missed question in the test. 422, electronic pressure control system. So I have, on page 49, I have figure 51 at the bottom. What the hell, that shouldn't be on the bottom. Guess I might have 2 different highlights. So figure 51 at the bottom, which is this one right here, pneumatic pressure control system. I have that highlighted as an online test question. Like I think they show this picture and then they say which what type of control system is this? What's that? It's not is it a test question?
practice test.
Well,
No, 22. It was about what you just talking about, though.
that's the question on how the valves fail, right? But they're gonna ask questions based on the schematic, just on the online test. So make sure you highlight this schematic and put online test question. Along, another online test question is the sentence that splits the columns on page 49. So all the way in the bottom left, the function of this control system is to maintain a constant pressure within a closed storage tank by controlling the positions of the nitrogen supply valve and an atmospheric vent valve. That's true of the electronic and the pneumatic one. That's bottom left of page 49. So bottom left, the function of this control system is maintain constant pressure within the closed storage tank by controlling the positions of a nitrogen supply valve and atmospheric vent valve. So bottom left all the way to the top right. See it?
It's in the right side, right?
Bottom left, so the bottom left.
Yeah, here.
So down there in the bottom left, that sentence starts, the function of this system is to maintain constant pressure. Be in the bottom left.
Oh, right. So, oh, oh my God. I still have the art from the movie.
Moving on to page 50. Still with the electronic pressure control loops, those last two sentences or the first sentences on page 50 are highlighted. In this control application, the supply valve typically fails shut on loss of signal and the vent valve fails open. This prevents overpressurization of the tank. So make sure the way the valves fail, make sure you have them related to either electronic pressure control loop or the pneumatic pressure control loop. Know how the valves fail. 430, which probably is the last section. 430, typical level control loops. Pneumatic level control loop. 431. The third and fourth sentence on 431 are highlighted. A flange mounted diaphragm type differential pressure transmitter, LT, measures the level of slurry, the pneumatic output of the transmitter sent to the level controller in a level recorder. So right here is my differential pressure transmitter, right? Where is it getting the two pressures from?
What's the question? What's the question?
So this is my level transmitter right here.
Right.
It's a differential pressure transmitter. So with a differential pressure transmitter, that's for level on a tank. Where do the two levels, where is it measuring the two levels from on this tank?
Control and valve.
Not the control of the valve. What part of the tank is it measuring from? Top and bottom. Because the bottom is going to be its most head pressure, and the top is going to be its zero. And sometimes this is called a leg or the high leg. This can be, I think we talked about in this class. If not, we'll talk about it next semester. This can be a dry leg or a wet leg. We talk about that.
Yes, sir.
So where this stuff, if this were to condensate or something was able to get in here, they would fill this with an inert fluid or whatever and cap it off, and that would be its zero. But for a differential pressure level transmitter, it connects to the bottom and the top of the tank. So level transmitter senses the level in the tank, it's recorded, maintained, goes to controller. Controller says, does this need to go up or down? If you can have a pneumatic booster, so that's saying this is pretty far away from the controller. So they'll have a booster right here with plant air connected to it, because you have to have quite a bit of air to move these valves. And then this will open or close based on what the level is in here. Good. Page 50, that last paragraph on page 50 is the whole thing is highlighted. Everything on page 50 is highlighted into page 51. So because the volume of air transmitted by the controller is insufficient to operate the control valve, a 1-to-1 booster relay is installed in the vicinity of the valve actuator to increase the controller output air signal. Elect 432 electronic level loop control. So same thing, but using electrical. Second paragraph of 432, second sentence is highlighted. The level controller compares the actual tank level to the set point and produces an electronic signal proportional to the difference between them. So same thing with this tank. Where is this level transmitter hooked up to? Top and bottom. So it senses the difference, then electronically sends it to the recorder and the controller. And then this is a motor operated valve. So you don't have to have any kind of air or anything like that. Everything is run off electronics. The immediate next sentence is also highlighted. The final control element for this control loop is a motor operated globe valve. So this is a motor operated globe valve. This is the final control element for this loop. Flow control loops 440. Talk about all that. So measuring flow. What is this right here? Orifice plate. I guess it's marked. Y'all talk about orifice plates probably over and over again, right? Orifice plate creates a high pressure on the upstream side and a low pressure on the downstream side. And we can connect a differential pressure transmitter to the upstream tap and the downstream tap, and then it can do calculations, and it can determine based on the hole opening and the pressures, it can determine a flow rate, right? So measuring flow rate, you can see the upstream tap as this laminar flow is coming in, it's getting constricted, which is causing the pressure to go up. On the backside of this, it's got all the area in the world, so our pressure is down. So my highlight, the whole second paragraph is highlighted in 441 on page 51. The whole second paragraph is highlighted, but I keyed in on the second and third sentence, and the last sentence are keyed in on. I'm going to read the whole paragraph, but the second and third sentence are keyed in on, as well as the last sentence. A variable head flow meter measures pump discharge flow. The differential pressure is created by the flow nozzle. A locally mounted flow transmitter senses the differential pressure and sends a pneumatic signal to the square root extractor. The square root extractor converts the differential pressure signal to a linear flow signal and transmits the flow information to an indicating flow controller, or FIC. The controller compares the actual flow signal to the desired flow or set point. If a difference exists, a change in the control pressure is produced that actuates the bypass valve.
What were the sentences that you said the key on?
Second and third sentence, and then the last sentence.
Thank you.
Page 52. So, well, let me talk about this right here. Like, this is what it's talking about. So this is what is this a symbol for?
Centrifugal pump.
Centrifugal pump. So when you turn this on, if this is not hooked up to a variable frequency drive, this is just going to run all out, right? Turn it on, contacts are going to close. This is going to run 100% all the way through this system. Well, the way that we can get this thing to, you can control it with this valve right here. So you've got, your pump requires a minimum flow at all times. I guess this pump requires minimum flow at all times. Flow sensor measures the flow rate. So measures flow rate. Transmitter sends data to the next stage. The square root extractor, all that does is make it linearizes the data, which means it takes raw information and turns it into useful information, sends that to the controller, and then it can open the bypass to control the flow. So if we have too much flow going through here, we can open up this bypass, and this bypass will bring the air back down through here or whatever it's flowing through here, and it'll recirculate, which will decrease the amount of flow that's coming out here. Make sense? So that's all, the square root, don't get confused by FY or the square root extract. All this is doing is converting data, raw data into usable information. So for 442 on page 52, the electronic flow control loop, all the way in the bottom left, that sentence that starts in the bottom left and ends in the top right of 52 is highlighted. The square root extractor converts the differential pressure information into a linear flow rate signal and transmits this information to a flow recorder and an indicating flow controller, or FIC. And then my last highlight for this chapter is the last paragraph, first sentence is an online test question. The power control circuit varies the average power to control pump speed, which ultimately controls the pump discharge pressure. So that's this one right here. You can actually control the speed of the pump with electronic flow control. As an online test question. Any questions? No, this is quite a bit, but you've got, like I said, you've got all of Thursday to get through this stuff. But that is all I have for tonight's class. If you have finished anything and if you want me to check your answers, I can go ahead and do that. I will put, so you'll have both of these recordings online if you need to go back and look at stuff.